So welcome to this second panel. The first panel was about big data in general, the big picture. And today we're going to try to be much more focused. So as a warm-up question, maybe I'd like everybody to just spend maybe a minute to say what do they think is the relationship between big data and learning, machine learning. Yeah.
I think it's obvious. The more data we have, the more we need to develop and understand the data. And for that, we need learning algorithms. We need tools to distill, filter.
So how are these tools different from the tools that we had already?
I think that what is unique for machine learning in that sense, and it's not present in statistics, for instance, is the fusion of probability theory algorithms, which is core computer science, data structures, and in some cases, knowledge from neuroscience. Mm-hmm. And this fusion is unique, I think, to statistical machine learning.
Okay. Leon?
That's a tough question.
Well, that's why you're answering it.
So, I'm start with an observation that we have more images than human can see, more text than human can read. And it's a bit contradictory because we know that humans can learn to see and read with a lot less text than that. But on the other hand, maybe we can do things with the data that a human cannot do. And the only way to do it is with machines because humans cannot do it.
Uh-huh. Okay. You're next.
Okay. So I actually can see the relationship in two directions. One is, of course, from the problem side of how can we handle such large quantities of examples, of features, etc. But I'm more interested in the other side, is how can we enhance the performance of machine learning algorithms using the external resources that are available on the web. You know, like we have huge amount of data, and existing algorithms can benefit from it. You know, by for example, adding features, adding knowledge into the algorithms, and therefore increasing their performance significantly.
Okay.
Yes,
well, though I'm a computer scientist, here I will play the role of faculty from Industrial Engineering and Management Department. And I think that big data, so it looks to me that the term big data is a trap for all of us that we should be careful with. In what sense? So machine learning for me was always statistics for big data. Ability to deal in reasonable time and space with problems of high dimensionality in the absence of reasonable prior, for example. Uh-huh. But it was, so for me it was always associated with the term big data, but implicitly. Uh-huh. Now it is associated explicitly, so the expectations of the users, of the customers, let's call them in broad sense, raised. So if yesterday the customers of machine learning were happy with getting to know what happens in the organization, given the data, now they want these tools to tell them what the organization should actually do differently. And I'm not sure, and Leon's story was exactly about that this morning, it looks like machine learning tools are not very well prepared for this challenge, for these expectations.
So basically you're saying it's not so much the size of the data, it's more the expectations of how to make the, instead of just classifier, how to make it actionable or how to interact with the...
I wouldn't say it is instead of a different, it's yet another thing we should take into account when we discuss machine learning in context of big data.
Okay. Okay, let me go to a much more controversial question. One popular approach, so one of the problems when you have huge amounts of data and you need to store them on separate computers is how much communication do you need between these computers in order to achieve the combined analysis. And one popular approach is that you basically do stochastic gradient descent in different separate machines, and then you just send the updates between the machines. Do you think that there are other general ways to basically do distributed learning on big data?
Yes. First of all, I think that you've touched a point of, your question stemmed from a paradigm shift. I think that it used to be the case that computation is expensive and communication is cheaper than computation. And I think these days with machines with 128 cores and lots of memory, computation is relatively inexpensive compared to the inter-machine communication. And I think we start to see an emergence of algorithms which are asynchronous and try to answer, currently partially your question. One example is a beautiful algorithm called Hogwild. It is totally synchronous by Ben Recht and Stephen Wright. They actually analyze a model where multiple processors write, in this case, into a shared memory model, but in a completely asynchronous way. And the need for this algorithm came from actually heuristics that seem to work well, including the deep architectures that Andrew Ng mentioned yesterday. So I think there.
So can there be a theory of these kind of algorithms?
So there is a theory of asynchronous updates in the shared memory model when the feature space is sparse. It's high-dimensional data, but each example has relatively few indices which are non-zero, and they are actually quantify this. So the question is, how do we analyze way more complex models like the deep neural nets? And even in this case, there were recent progress by 3 Israelis actually, where it's not necessarily the distributed facet, but I think it will lead to better distributed algorithms.
Is the algorithm that you were talking about yesterday, the distributed boosting, is that something that has a lot of communication or limited communication?
We try actually to minimize communication, and for this reason we actually moved away from stochastic algorithm to a deterministic one, and shard the data. So basically the data is funneled to each machine completely in parallel. But it's more of an engineering effort than it's principled from the engineering sense, but it's not a concrete theoretical progress.
Okay. Leon, anybody? Yeah, go ahead.
I would give it a shot. Again, I don't think that in this particular direction I can add anything to what Yoram said, but big data, we perceive it as a synonym to stored big data. And in principle, it doesn't have to be the case. Now, there is a motivation in the industry for this big data to be actually stored because the cost of the storage goes down. And if you want to maintain it as a business, you want to sell more storage.
Okay.
Now,
what's the alternative?
Alternative, for example, can be, alternative to storing is not to store. And when we perceive distributed machine learning as, okay, we have data partition between different machines, the storages, and then model, like weak model is learned on each one of them on part of the data and then somehow aggregated together. It can be the other way around. The same data is broadcasted to all the machines. Then each machine is responsible for part of the model and nothing is stored at all. Now, of course, that is an extreme. But in principle, that is yet another conceptual way to parallelization of big data processing.
But
now, whether we're ready to do
that would maximize. That seems to really increase amount of communication.
First of all, I'm not sure that, no, not necessarily. The question of what part of communication costs. I'm not big expert in networking, but there is a difference between sending a big chunk of data on the network between two machines and having the same bit of information, for example, distributed between the machines via memcache. The costs are different. So I'm not sure that paradigm of let's split the data between the machine and aggregate the learned model is the only way to go.
Okay, I mean, that was from yesterday, but from my experience, my definition of big data is simply data that is easier to put in a box and FedEx instead of moving on the internet. Because if you try to move a terabyte from where I live in San Diego to San Francisco, it's going to take you several days on a fast network. True. And if you send it on FedEx, it's going to be overnight. So I think that there is a very, very real limit to how fast we can.
You meant peta.
No, tera.
Tera by now is
fast,
cheaper to
okay.
and faster.
All right, so let me just tell you a story. Okay, maybe that would. So I basically decided I want to look at the census data from the Census Bureau. And I told people, and people said, that's big data, that cannot be big data. And I said, okay, but let me just try to download it. And so I downloaded on the fastest line that there is in San Diego. I don't know what they have on the other side. It took for 1.5 terabyte, it took about 3 weeks.
Okay.
And so within Google, there might be amazing rates, you know, but if you're talking about long-range transmission of information, I think that to get beyond like 10 megabit per second is very, very hard. Costs a lot of money.
No, we're splitting hair here. The question whether it's tera or peta is immaterial.
Okay.
When Google had to move its data center from Oregon to Alaska, it was done not using FedEx, but with
trucks.
In trucks.
Yeah.
Actually, your definition is the first testable definitions I've ever heard.
Yeah.
You can test either it passes
Right.
or not.
Yeah, you can try to move data. So we have a perception that the internet is extremely fast. In fact, it's you know, the resources are not there to really make it fast. So.
No doubt about that. The question is whether this is the bottleneck for most of the businesses that want to analyze their data. Is it really placed? But again, Google may have farms in different places in the United States and in Canada.
Right.
But if I'm a small, medium-sized business, this is not the case. Usually, I don't even have my own farm. I store my data and my computing power on Amazon or Azure. So the really issue of communicating tons of data from Alaska to Oregon is not an issue for me.
Well, terabyte is something that you put on your desk as a regular thing. To move a terabyte, let's say that you're just an enterprise, you just sell shirts, and you have, you know, stores all over the United States, maybe 300 stores. You can easily generate, you know, a terabyte on all of these places, but you don't even want to bring it all into one place.
Exactly. And it's not necessarily the case that each and every bit of this terabyte have to go to each and every server that is, for example, responsible for some part of the model. So, for example, suppose that some server is responsible for certain feature, and it is known to be responsible for certain feature. Again, I'm taking to extreme just to exemplify the idea. Then only data that has this feature present in it should be sent to this specific server. So again, if we'll have to pack the data in terabytes and then blindly send it to each and every machine, then of course it will not be a good idea.
Right.
But sending it selectively and then storing or not, depending on the decision of that machine, is something that we should consider.
Okay. Yeah, go ahead.
Something I'm confused about. Can I ask a question?
Yes, please.
I'm confused about this story of communication versus computation because, okay, I understand communication between computers, computation inside the computer. So I open the computer and I see memory, processor, and what it does, it's just communicate stuff.
Right.
So I say it must be in the processor. I open the processor, I find plenty of wires.
Right.
And most of the work there is shuffling data around.
Right.
So computation is communication.
Well, no.
There is a difference in scale.
I mean, I would say that there's two quite separate disciplines. One is information theory and one is computation, and we absolutely don't think that if you can. We used to believe that communication is completely negligible. in terms of the complexity of the algorithm. Now we're stopping to think that. It just, that's all it is. But it's true. On every level of the computation, communication is actually the bottleneck.
So the question is, this debate between communication and computation, is it a fundamental debate, or is it an artifact of our technology, which has these gaps in scale between what's in the processor, what's in the box, what's between the boxes?
I think that it is fundamental in that it basically, in order to continue doing more computation, you need to do it in highly parallel way. And in order to do it in highly parallel way, you need some kind of communication between the pieces. So I think that that's kind of where things are going. If computers would continue to go twice as fast as they used to maybe 8 years ago, then there would be maybe no issue, but they stopped. Yeah, go ahead.
May I make a side comment?
Yeah.
The panel so far reminds me of a TV show that was popular before I left Israel 8 years ago called Popolitica.
Aha.
Where the moderator would ask a question and then the politicians or whoever would answer whatever they want.
Right.
The only difference is that we don't shout at each other.
Aha.
So either we'll start
let's
shouting
start
at each other or we'll stay on target because I feel that we don't answer your
Well, I can tell you that my marching orders from Ran was, if they start shouting at each other, it's a big win. So, yeah, that's the idea. So let's see. So a related question maybe is, tomorrow we're going to hear from Dan Aron about sublinear. What? Next hour, right, sorry. Next hour we're going to hear from Dana about sublinear computation or sublinear approximation of graph properties. Sublinear is an interesting idea. It's basically the idea that you throw away a significant part of your data. So do you guys think that it's time to throw away a significant part of the data?
Definitely. Most of the data is crap.
They actually do.
Well,
yeah.
The question is, how do you do it?
Okay.
Because if
Randomly.
you believe that data is independent, identically distributed, you have no way to know which one is which. You have to look at it all.
Uh-huh.
So if you assume that the data has, you can somehow sort it at the beginning because it comes from different sources, then you have the means to start selecting without looking at everything.
Okay, so let me weaken it somewhat and say you're allowed to look at everything, but you are not allowed to keep everything. You're allowed to keep only a very small fraction.
Then it's going to hurt in quite a few applications.
So please.
For example, online advertisement. The space is very high dimensional and data comes all the time. Now, if you will decide to throw away some data, what you will get is lots of ad spam. Mm-hmm. The reason is that we don't just learn. We actually, the systems that do online advertisements and prediction, and they memorize as well. Okay. And you can actually say, I would like to improve the memorization in terms of compression schemes and lossless compression schemes. But if you'll throw it, you'll start to see that, every time you'll type in virgin oil, you will get an ad, would you like to marry a Persian wife?
Because you threw out data.
Yeah. The first 10 examples of that query were actually answered with, you got an advertisement of that sort. Uh-huh. And after 10 examples, you memorized actually that this combination is of this advertiser and that query.
I see.
Right? And otherwise you will be annoyed because you want to search for a virgin oil, not a wife, I assume.
So you're basically saying, no, you shouldn't throw out.
There are settings where sampling is really hurtful.
I see. Okay. Well, you said that yes, so please.
Yeah, because first I must tell you a story that my first ever published paper was in machine learning conference in '88. and the title was The Role of Forgetting in Learning.
Uh-huh.
And my thesis actually was about information filtering in learning systems. And I see again and again how too much information can be harmful from all various reasons. It's not, so the fact that humans are so good at filtering information and knowledge showed me some, that I think it shows that this particular direction has some advantages. If you ask me for the particular, for big data, why do we need, can we look at part of the data? If you look at, if you look at learning curves, for example, in many problems that I looked, learning curves start to straighten and thousands, asymptotically, maybe 1,000, sometimes tens of thousands. I see very rare cases where you keep on seeing increase in the performance. Maybe Yoram did in Google, but I didn't see it in any applications that I did.
I see.
So I don't think that, I don't think, I don't know, maybe you did. I don't know if anybody here, so, learning curves that keep on going up after tens of thousands or hundreds of thousands of examples. And it means that it's not that we don't necessarily need. The fact that we may have millions or billions of examples doesn't mean that necessarily we have to use them. It can have some harmful effects as well.
I see.
Yeah.
So, so do you think that this is even true when you're talking about text with ZIF distribution?
In text, yes. In text, we need to be, I think we need to filter examples. I need to filter, well, everybody, most people here will agree that we have to filter features. We saw it again and again. Again, I don't know, Yoram talked today about, yesterday about how many features? You talked about billions of features? Yoram, in your lecture, yeah.
Pardon?
You said, you gave examples yesterday. I saw the numbers, like billions of features. You said, I don't remember, something.
10 billion of features, yeah.
Yeah. So I know, again, from our experience, even algorithms that are supposedly supposed to handle a large number of features can benefit a lot if you filter features. We've shown it again and again. So I think filtering and selection is important. That's what I'm saying. I'm saying that the fact that we have much knowledge doesn't mean, or information doesn't mean that we have to use it.
So which features or which examples do you recommend removing, or what's the general rule? So talking about the algorithms, the general problem of feature selection is a hard problem. You know it. Like, okay. Currently, people use the other extreme. They use very simple feature selection algorithms that are just filtering approaches. And the question is, what do you have between? You talk about using resources, parallelization. One example of using this parallelization is, for example, to select a good subset of features. There are various algorithms to do it, but that are between, that are not exponential, but that can use, but are not linear. They can use as much resources that you invest in them. And in general, I think that the whole process of learning, especially when you talk about big data, is much more complex than what we're doing now. There are all kinds of processes that we didn't even talk about. Feature generation, feature selection, example selection. We can have anytime algorithms for learning. We can have parallel ensembles of learners. We can have parameter tuning. For each of these processes, you have parameter tuning. You can invest as much time as you want in parameter tuning, which is many times is more helpful than the processes that investing time. So eventually what we have to do is to employ a very complex system, compose those many components that have to be distributed among various machines and have to be managed, and the resources must be distributed in a wise way. Okay.
And, so
it's complicated.
It's
complicated.
May I ask,
yeah.
Actually, this is half question to Yoram, because it sounds that, so I think that most perceive machine learning as generalization. And from what I hear, and I completely agree with Yoram, that in Google, for example, and in some other use cases, the artifacts of machine learning algorithms are used for control. So it is not only for analytical purposes. I will give you a simple picture of what happens in your organization / physical process, but I also give you a tool that will allow you to control your organization well. For example, catching phenomena that really would disappear if only the only thing I care about is to generalize the process of advertising on the web. If I really care about if billions of features are really important, we talk about the level of user ID. Are these really features that can be used, that are important to generalize some important notion?
Well, I should steer away from the specific setting. Maybe I went too far in terms of the internals, but let me sort of give another example, speech recognition. We have now a lot of speech data. Every time you speak, you use, say, Siri, and it doesn't recognize you and you correct it, it's a supervised example. What do you do with this data? Do you throw some of it? The answer is no, because there is we have a heavy tail distribution, ZIF distribution, whether it's text, spoken language, or written language, or visual language. There is always going to be a new accent spoken through a new cell phone, through basically different communication channel, and we need to learn it. So you might call it anecdotal cases, but it starts with anecdotal cases, and you cannot generalize. But as more data comes, you start generalizing. And what we see is that we do need to actually store that data. I might be controversial or hopefully not offensive, but I think that feature selection is dead. I mean, feature expansion is now the word.
Yeah.
Yeah, I think I have something to say. If you take a fixed problem with a certain input, a certain output, a fixed task, there is a base error. It's not 0. So let's say it's 10%. Take 1 million example, you get 10.1%. Okay, 10 times more money to the problem, you get 10 million examples, you get 10.01%. Okay, 10 times more money, 100 million example, 10.001. So at some point you should stop. So that means that no single task justifies expanding the data to the infinity.
Well, no single binary task. No single binary task.
Except, I'm coming to something like that. Except that this means that at some point you should do something else. And the fact that you have a lot of data means that you can address a lot of problems. What Yoram describes is that he wants to keep the speech recognition extreme cases. Now, there are not so many extreme cases. In terms of average performance, it's not going to change that much. But things could change. You want to know it. So it's a change in focus. You no longer want to focus on optimizing some average performance for a distribution that you don't even think is going to be the same in the future. You want to optimize the breadth of your system. It's not really on this data set what percentage of phonemes I'm going to get completely right. Is how many people are going to be recognized correctly?
Well, if you're a French person, for the sake of the example, who visits Israel and uses Orange for the first time in the local Android phone and it doesn't recognize you, you will be annoyed, right? So is that a corner case? Yes, but you want to cater not just to the masses, you basically.
Because you're not trying to recognize phrases, you're trying to satisfy users.
Right.
It's not exactly the same thing.
No, I agree. I mean, you can think in a way about these massive data as really just combination of many smaller distributions, right? You have the distribution of the people with Israeli accent. You have the distribution of East Coast accent, West Coast accent. You have distribution, finer and finer distribution until you get to the individual person. And so I think that, you might, the tail might just grow to be something much, much bigger. But still, I think that there's a different thing. There are clearly data points that are clearly just in the center. They're in the very dense part. I mean, that's the definition of very dense part. So can't we throw a lot of those?
For sure.
Uh-huh.
Yeah.
Okay.
But I disagree that we need to satisfy some, user intent, but that's what machine learning in many cases is about, right? We keep inventing and generating new crap. After the iPod, we had an iPad, and for 3 hours, every query that said iPad, say, did you mean iPod? And it's unavoidable. So yes, we deal well with the, say, popular queries, the standard accents, the standard text, but it's really mostly about the tail. We're done with, not done, I mean, there is room for improvement, but what you call the centroids of the data are, something that we,
So is your view that basically Google will keep all of the data forever? What about...
First of all, it's not Google who keeps the data.
Whatever.
It's the Internet Archive, for instance, and other organizations.
Okay.
Unfortunately, the large search engines, Bing and Google, use lots of SSD, which means that the data will disappear.
Right. So there is some data, in order to overcome that, there is some data that you need to basically replicate, keep replicating. So there has to be a selection process, whether you want it or not.
The data we need to keep is called Britney Spears.
It's called what?
Britney Spears.
Okay.
It used to be one of the most popular persons.
All right. So how are we doing? By the way, if somebody from the audience wants to ask a question, you're welcome to. I see a microphone there.
It's for Yoram. Can you elaborate on feature selection is dead? I think this is what you said a few minutes ago. This is what I wanted to ask you about. I mean, machine learning and big data for the masses, like a McKinsey report talked about the amount of data scientists that is going to be required in a few years. And I think most of these data scientists are going to do feature selection, I think.
Yeah, you should answer.
I would like to give a factoid. It's not even big data. It's a couple years ago, Isabelle Guyon organized a feature selection competition. And the winner was Radford Neal with complex Bayesian neural nets. Their main particularity was they didn't select features. They used them all. So, yeah, you might wonder whether feature selection is something you really want to do. You might have reasons to do it because they're expensive. But
I mean, Professor Etzioni yesterday talked about listening to your data and so on, which is basically another term for feature selection, right? I mean,
listening to...
I think there is a confusion between feature selection and feature engineering.
Okay, sorry, not feature selection.
That's a different story.
Okay,
Yeah.
I was
So
meaning
what are
feature
features
generation, actually, yeah.
Is one
Sorry.
story and feature selection is another.
Right, so basically feature engineering in a way is the opposite. It's basically you have raw data that you're collecting, and now you need to basically do some initial transformations of it.
So
and in general, my recommendation to my students is do them all. Do them all. Let boosting afterwards choose the good ones. So, and there are other ways to do it. But in general, yes, I do believe that feature selection has kind of outlived its useful life.
Okay, so let me just push it just a bit, sorry.
Yeah.
So feature generation.
Yeah.
So yesterday, Professor Andrew Neg talked about an universal machine, deep neural networks for feature generation. And Mr. Zinger talked about massive scale, Google scale, using them all. But I guess a lot of enterprises are looking for big data and machine learning without resorting to Google scale resources, which will naturally require hand-generating features. So is there I hope I made myself clear.
No, I think that there's feature engineering that you do based on your prior knowledge. Okay, and that's one type. The type that you're talking about, Andrew Ng doing, or deep networks, reconstructive networks, are basically that you're using unlabeled data so that in order to design features. So that kind of data is is cheap and plentiful, and so that's what is done there. And of course, it's not enough to just throw in a very huge amount of features. Some of them have to be actually good. So, but the point of trying to select which ones are good based on the label data, that's in general not a good idea, just because there's better uses for the label data.
But that's not what, what you're saying is not really founded. I mean, there are many cases in empirical studies that show that feature selection can help in. So the algorithm is not sophisticated enough to overcome the redundant features. That's what I'm saying. So okay. I use also to say let the algorithm decide what features are necessary and what not. But okay. Apparently, most of the current algorithms are still sensitive. Even SVM are still sensitive to redundant features, and we show it empirically quite a few times.
Okay, I'd like to see the study.
And there are also parameters that, again, some Microsoft / Google and others care less about, but there are organizations in which the traffic is much lower than in Google, so the amount of training data is much lower. And second, and they need the deliverables of machine learning very quickly. So not a lot of data, it should be generalized. So the only alternative is to reduce the number of features, otherwise.
Yeah, but the question is, do you reduce the number of features as a pre-step to the learning algorithm?
I would prefer not to do that, but if I'm very constrained. So suppose I have only one example, okay? 5 examples, okay. 10 examples.
Okay.
Then no matter what machine learning algorithm I will use,
right.
It will not help me if I have
right.
10,000 features.
Right.
So this is the balance. What might be the case that in some organizations, the amount of data is not that large in comparison to the number of features.
Right. Yeah. I mean, no, I don't think that problems with very small amounts of data are going away. It's just that it's much cheaper today to actually collect much more data.
That's true.
Yeah, but also the feature generation actually is going to even require us even to do even more extensive feature selection, because if you have, for example, feature generation actually allows many times to have infinite feature space, and then you need much better feature selection algorithms. If you can generate features, you say that your student, you ask them to do all kind of combination, feature combinations they can do.
Right.
This space is actually infinite, so
no, it's not infinite because our computers are not infinite. But
yeah.
but I'm just saying, basically what I'm saying is, don't worry about overfitting. That's not the place to worry about overfitting. That's my belief. Okay. Yeah. Question.
Let me throw something also controversial on you, and I'm really interested to see how you're going to respond. So machine learning is all about generalization, such that once we see a new example that we haven't seen before, we will be able to deal with it. Here's the problem. In big data, we can say that we have seen everything. So once we see an example, all we need is to find that example in the data that we have already seen. So doesn't it boil down to search? Isn't the machine learning in future just information retrieval?
He's asking me again?
Yeah, okay. I mean, I'll give you my answer. I think that the answer is simply no. It's basically that you can have, petabytes and petabytes and petabytes, and the new example that you've seen, you haven't seen it before. So I think that that's the natural cases, right? So if you look just at images, there's enough space there to basically have all of the computers in the world filled with images, and still a new image wouldn't be there.
I mean, the world
How about
is
text?
changing.
What do you say?
How about text? The language doesn't allow us to use expressions that are not used in the language.
Well, I think that people also in language continue to invent new words constantly. But I agree with you that it's a relatively smaller space. If you ask me about, how much of the big data 10 years from now is going to be text, I don't think it's very much.
I think that, data is rapidly growing, and quality data is rapidly growing. Look at Amazon's data, for instance. People buy more products, people invent more products, people have new deals, and all of this is data. I'm sure that Amazon doesn't throw his data. Moreover, maybe we are מדינה קטנה מוקפת אויבים, so we don't use S3 and EC2 and Azure, but you can have actually a small startup with 3 people that deal with petabytes of data while having 3 laptops and a small office space. So the world is changing, and things. And again, I might be abrasive, but things like anecdotal feature selection, large-scale sampling, throwing away data, not sampling from an algorithmic point of view, I think are passé.
Yeah.
So I have 2 answers. The first one is about, at some point we see everything. It's not what we see. If you take a data set of queries, for instance, so you take 2 weeks of queries, and you observe that about half of your distinct queries are unique. So okay, I take 1 month of query, and half of your distinct queries are unique. You have more of them, but still half are unique. Okay, let's take 1 year of query. About half of the distinct queries are going to be unique. So no, we haven't seen everything. For some reason, the world is larger than the computers, and that's good. The second one is about what Yoram said. In the traditional machine learning, the mode of thinking is how much model can I pay with my data? And for this reason, you need to make the model simple because, how much model can you pay with your data? Can you pay for your data? And now it's changed. It's how much model can you pay with a certain computing budget when the data is infinite. And that changes everything inside. It's not the same compromise. Like, for instance, you can use a faster algorithm that do less work, but they're going to see more data or maybe some unlabeled data and do things that are more interesting because you have the data and you're going to make it fit in the same budget. So you're no longer in a situation where the model is constrained really by the data size. Then what you're going to do is going to be constrained by the time. So the algorithmic part becomes very important. And also, you can use more data and maybe different data, which you wouldn't do because you wouldn't want to increase the model complexity with the limited set of labels. But it's changed.
One thing which was not really discussed, I think, and is important, related to the talk by Andrew and yesterday, is the question of architecture. Biological systems, a young baby by the age of a year, he sees, an infinite amount of unlabeled data. And he has this kind of, and the point is that the architecture of his brain is not a general purpose computer, it's some very specific type of architecture which seems to be playing a very important role in the efficacy of learning in children, in animals. And this is something which no one really discussed, the question of the architecture and the adaptivity of the architecture, and maybe devising specific architectures for specific types of tasks. And I wonder what your thoughts are on that.
You're right.
Yoram.
Again?
Yeah.
I think it's an excellent comment, and I think we should pay more attention and actually learn from biological systems. Just recently, Jeff Hinton, who is very original, not a mathematician, came with a brain-dead procedure called dropout, which people now started to try to analyze, which improved actually the performance of deep neural networks by an order of magnitude. It can be viewed as a sampling procedure that forces diversity between neurons, basically, so that neurons will not cooperate and will actually cover different parts of, say, their visual cortex, for instance, right? So the architecture and the synapses, the communication channels are really important, and there's lots of room here actually for cross-fertilization. I think that human learning should be actually inspirational for new algorithm.
Yeah, I would use the answer used yesterday by John Denker, that basically, whatever, my algorithm, boosting, is the second best algorithm for any problem. So, exactly. So, and the point is basically that what we have, because we're really dealing with a much more diverse set of questions than what a baby needs to do in, early on, then we're giving very generic kind of answers. And if you really want to do some specific task, then yes, you need to decide on a lot of specific things.
The baby can do lots of things.
Okay. No, I'm not saying that the baby. I'm not saying anything about that. I'm just saying that the specificity of what the baby is biased towards comes together with the world of the baby.
I like very much to look at the architecture of the human mind, but I don't think that we have to look at the architecture of the human brain. And I know that some people here think that the way to go is to look at the architecture of the human brain to achieve what we like to achieve. And some other people think that we don't have to look at human at all. We just have machines and we have to do whatever we want to do. I think we can learn a lot from the architecture of the human mind. But I think that the von Neumann architecture, hardware architecture, is enough for achieving everything that we need to achieve. I don't think that we are restricted by architecture today. That's my opinion.
So I have a question about the real-time consideration of designing an algorithm. So you can learn with big data for, let's say, an hour. You have a lot of machines and you learn some model, but then you have to apply it in real time, like to detect something in a video, to push ads, for example, or any other ideas. So do you have still the same considerations of all features should go into consideration, or maybe the real-time consideration here does affect what we will choose at the end? Oh. Also the algorithm itself.
Well, I mean, there is a very good example of Paul Viola's face detector that is now old work, but that is very effective. They use boosting in order to build the classifier, but then the classifier, even though it was as a potential given a huge number of features, it selected much less of them. Beyond that, they use cascade and all kinds of other methods to make it work in real time on video. So it's definitely not the case that you have to have all of the features used or having significant weight. You can actually remove them, but just the question about feature selection is, how do you do the feature selection, right? Do you do it by the machine learning algorithm, or do you do it by some a priori kind of rule?
But I think that it's a very good comment, because yeah, serving an inference is likely to be done more than learning, and the need for efficient serving, real-time serving, is a real need. So there was a talk by Miki Elad that directly and indirectly touched it. There is a whole community, compressed sensing, and also in machine learning. There are all cottage industry of sparsify this, sparsify that, but there is a good reason for that. What you want at serving time is to actually find not necessarily the best model in terms of generalization, but the best model in terms of generalization and, say, memory and bandwidth constraints. So things like applying L1 regularization is not necessarily the best tool in terms of in theoretical tool in terms of generalization, but it will give you very good results in terms of obtaining compact models.
Okay. So, Yoav, maybe if you have one final question to the panel, or we should wrap up, or
let me think.
One round.
So yeah, so actually I have a question. Somebody asked me earlier. It's kind of an interesting question because we all say, oh, everybody, any little startup can have their own petabyte. That's true, but you know, most petabytes are actually very expensive. Somebody collected them. So is it really, so when you want to start a company like that, it seems like the only serious option of doing it is either partnering with Google or Microsoft or something like that, or by really collecting the data yourself. So it's not like there are out there data sets that are you know, terabytes that you can just download. So what do you guys think?
Well, if it is a startup that does its own business, they have to collect their own data. I mean, I think there were two questions there in one.
Okay.
One, whether it is feasible for a startup to become a big data analysis startup.
Right.
And two is whether big data is available for experimentation for...
Yeah, I'll make it more specific. Like as a business proposition, if you want to get into startup, into commercially, into big data, what are the hurdles? Is getting the big data a major hurdle or not?
Well, with the companies that I had interaction with, big data is an artifact of the business. So if the business is serving, say, millions of users, and the data is collected, you automatically get tons of data.
Okay.
And if it is not, then you don't need it.
Right. Okay.
Well, I think it depends on what kind of problem you'd like to do. If you want to do search, then you have basically limited wiggle room compared to, say, Google. If you want to do online shopping, then Amazon, and in fact, Amazon has the largest, I think, amount of interesting data. It's hard to compete. Or if you, say, Microsoft, you want to play the Kinect. Okay. But there are voids there. Like, think of a startup like Waze. They have very useful data. Before that, there was YouTube. So you can collect lots, huge amounts of useful, meaningful, high-quality data if you find the right void, and right. People will find voids.
Right. No, but I'm saying, I think one thing that it makes me aware of is that when you think about such a thing, it's not so much that you go and find data that is lying there. It's more that you have a really good idea about how to collect really good data. And then you also do big data analysis.
I completely agree.
Okay. That's all. All right. Thank you very much.
So thank you very much to the panel.